let's make a start. Quite a few announcements before we get into today's material. The first is that, so following the Tuesday's lecture that William gave about the San Francisco earthquake and fire, now is the time to be working on assignment number 2. And assignment number 2 is due on Tuesday. Okay, so in however many days that is, 5 days. I want to make sure you're aware of the fact there's a lot of work coming up. This assignment is due on Tuesday. Second thing is that your field trip report from the field trip over the weekend is also due on Tuesday. Okay, all of the information about what you need to do for that field trip report is on the web page. Is there a question? Uh-oh, we've had a complete... Did I make a mistake? Is it true that these things are due on Tuesday? It's just that Tuesday's the 30th, not the 2nd? Okay. The 2nd is Thursday? Okay, so you'll have to make a suitable adjustment to the next slide, which is that the midterm is next Thursday, which is not the 4th. It is, in fact, the 2nd. Sorry, we obviously had a failure of something this morning. So, yes, so the point is that on Tuesday, both the assignment number 2 and the field trip report are due. And then on Thursday, which is in 1 week, and not 1 week and 2 days, sorry. Okay, on Thursday is when the first midterm is. Are we all clear? So the homework and the field trip report are due on Tuesday, okay, and then the midterm is on Thursday. The midterm will be in here, will be in this classroom. The midterm, what will be covered on the midterm will be everything we have covered up until the midterm. So that includes today's lecture, it includes Tuesday's lecture, it includes the first two assignments, it includes the field trip material, it includes everything up to the moment of the midterm. Okay? Yeah. The readings, yes, you are expected to know and understand everything that we cover in the class. That includes lectures, it includes reading, it includes assignments, it includes field trips, everything. Yeah. I mean, yeah, we talked about Katrina in the 1906, that includes them. I'm not sure, is that the question? Yeah, absolutely, includes everything we covered. Yeah. So the question was, even the case studies in the book that we haven't really talked about. So it includes everything that we've covered, which includes the class, the reading, the assignments, and the field trip. Okay? I hope it's coming across, but don't worry, I'm going to come to your question. So then your question is, what is going to be emphasized? Okay, that's what you should ask the professor. What is going to be emphasized? I can tell you that I will emphasize what we have talked about in class. That does not mean that there will not be questions from other parts of the material, including the readings. However, I can tell you that I will emphasize what we've covered in the lectures, and the reason for that is that what we cover in the lectures is the material that I consider to be the most important. So obviously I'm going to emphasize that in the exam. Yeah. Oh, yes, I didn't write that down either. Sorry, it's been a bit of a morning. Yes, the review session. So let me go through this. So the format of the exam, it's basically, actually I'm not going to say because I'm going to make a mistake. The format of the exam you can find, if you go to the organizational tab of the class webpage, you will find some example questions. And those example questions are on sort of a blank version, as it were, of the exam. So you can see what the format of the exam was. I hope I'm going to get this correct. Maybe one of you guys can tell me if I get it wrong. 30 multiple choice, 20 true-false questions, and then you're asked to answer 1 of 2 longer questions. That's the format of the exam. Okay? And then the last piece is that there will be a review session. It will be on Monday at 6:30 in 10, sorry, I forgot to write down 10, in 10 Evans Hall. Yeah. No, the exam will be 1 hour in duration. Okay? The exam will be in this room. On Tuesday, I'll talk about how we're going to handle the exam, so you know. Any other questions? The review session, you should come with your questions. The GSIs will not be coming to the review session with material that they're just going to present to you. They are simply going to answer your questions. So if nobody has any questions, the review session will be over. Okay? So please review the material ahead of time, and then come to the review session with your questions, and they will happily talk about the stuff you're asking about. Yeah. Do you need a calculator to do logs? So we haven't done logs yet, right? Oh, assignment 2, right, okay. So yes. You will need the same materials that you needed to do any part of the class, including the assignments. Any other questions? Yeah.
Is the intensity scale only on the PowerPoint for Tuesday?
Sorry, second? Right.
Is it only on the PowerPoint?
I'm not sure what you mean by only on the PowerPoint, sorry. The intensity scale? Oh, is that what you're asking? Oh, okay. So the question here is, where can you find the Mercalli intensity scale? You will find it in your textbook, but also you will find it, the Mercalli intensity scale, I'll tell you where I always get the Mercalli intensity scale from, is on every single shape map that the USGS provides for earthquakes. And we looked at the shape map at the beginning of the class following the Napa quake. We looked at several shape maps, actually. If you go to any of those shape maps, you will find a nice little table that lays out the Mercalli intensity scale. When it comes to the actual the text, the descriptive text associated with the intensity scale, then of course the lecture on Tuesday has most of that, and then you will also find it in your textbook. Ah, yes, actually William, I realized that, or rather I realized it, William had already realized it. The lectures from Tuesday, the notes will be posted shortly after today's lecture. Any other questions? Yeah. Again? Do you need a Scantron note? You don't need a Scantron or a Blue Book or any of these other things. You need a pencil. Okay? Move on? All right, great. So the point being, I just want to make sure you're all aware that there's a lot of stuff coming up for the class. There's the assignment due on Tuesday, a field trip report due on Tuesday, and the midterm on Thursday. Okay, I don't want anybody to be caught out. Of course, all of this information is on your syllabus. Okay, so we're now going to start to talk about the earthquake process. We spent a lot of time talking about impacts of earthquakes, and then we spent some time talking about faults. And now we're going to transition into talking about the actual locations of earthquakes, where earthquakes, occur. And so just, it's obvious, but the connection between faults and earthquakes, it was only really made after the 1906 San Andreas fault. They just remind you of that. So that's barely 100 years ago. And so that's really very recent. It's such a fundamental observation that earthquakes occur on faults and that we can map faults at the surface of the Earth. I mean, it's so fundamental, but it was only really recognized after the 1906 earthquake, so relatively recently. But this, obviously, the schematic just shows a fault. This is a thrust fault. It's a mountain-building fault. And so when an earthquake occurs, some portion of this fault slips. And so this mountain range, of course, the fault must extend all along the mountain range and it extends down to some depth. And it's not that the entire fault has to rupture, but some area on that fault plane ruptures, and that's what generates the energy that then gets radiated out from the fault, and that's what the earthquake is. Okay, so that's the connection between faults and earthquakes. Yeah. So the question is, when continental plates collide with one another, they form mountain ranges and they're bigger, and how does that relate to these thrust faults? It's the same thing. It's the same process. So when two continents collide with one another, they form thrust faults exactly like this. And there may be a whole slew of them over some large area, which is why you get mountain ranges over large areas. But it's all the same process. Okay? We'll actually talk about this in more detail on Tuesday when we talk about plate tectonics. We'll talk about plates colliding and mountain belts being created. Okay, so when it comes to asking the question of where earthquakes occur, I want to start by stepping back a little bit and thinking, when we talk about earthquake processes, these earthquakes, the ones we really care about, often only come around on a decadal timescale or on a timescale of hundreds or even thousands of years in some places. And so we need that historic information. So we need to know where earthquakes occurred 1,000 years ago, 2,000 years ago, ideally 100,000 years ago. And so this is a real challenge. Of course, we can use geomorphology. We talked about the geomorphology in Wallace Creek. We can use geomorphology to tell us something about past earthquakes. But the much better record, of course, is the historic record, the written record. So when it comes to talking about the written record for earthquakes, how much information do we actually have? And it's a simple question of what is the total length of the written history in different parts of the world. And so this varies, of course, significantly around the world. In China, we have written records that go back to about 780 BC. In Japan, we have some records from about 400 AD, but really the record only starts at 1600 AD. So this is all for me, as a geologist, as a seismologist, this is a really short timescale. We talk about geologic processes that occur over millions of years. And we're talking about having a few hundred, well, in this case, almost 3,000 years. But in this case, we're talking about 1,000 years. This is a really short time frame that we actually have information from. Greece, this sort of section through here, which has a lot of earthquake activity, we have records back to about 300 AD. Okay? And of course, in California, we only have records from the mid-1800s, so very short time history of the seismic activity in California. And that's why we go to places like Wallace Creek and we do the paleoseismology in big trenches and try and reconstruct as much information as we can that way. So this is kind of what we have to work with. These are the records that we have available to us, and as I say, it's really quite limited. But sort of coming up to date and looking at the historic record in the more immediate past, essentially this century, we obviously see a lot of information. We have a lot of information about past earthquakes. And I just kind of want to remind people about the scale of the problem. So going back to the beginning of the century, the first big earthquake was in Bhuj, India. That's what is shown here. 20,000 people died in this earthquake. Bam, Iran in 2003, 30,000 people. Sumatra, almost 250,000 people killed. The majority were killed by the tsunami rather than directly by the earthquake. But of course, the tsunami is one of the products of the earthquake. Pakistan, 86,000 people were killed. Sichuan in China, 88,000 people. Haiti, over 300,000 people killed. And then Japan, the magnitude 9 earthquake and tsunami in Japan, 20,000 people. Okay? So this is the more immediate written history. And it has, so what this means is that this century, approaching 800,000 people have been killed already by earthquakes. Okay, that's a very big number. So what about in the previous century? So we have pretty good records for the 20th century, so we can do a reasonably good job of estimating the total number of fatalities from the written record for the previous century. And so the height of these bars shows the number of fatalities. And so, of course, the biggest here is the Tangshan earthquake in China, and it's very unclear how many people were killed in this earthquake. The official report is that there's 250,000 people died, but various agencies have estimated that it was closer to 500,000 people killed in that earthquake. K is 1,000, right? So this is 250,000 to 500,000 people. This was in 1975. Two big earthquakes in China, about 20,000 people each. The 1922 Tokyo, Japan earthquake, 143,000 people were killed. That earthquake actually is what Japan is probably the most earthquake-ready country in the world. Okay? The fact that on the previous slide I showed you that there was this magnitude 9, the Tohoku earthquake in 2011, magnitude 9 earthquake, huge tsunami. There were still 20,000 people were killed, but that was a huge earthquake. And the fact that only 20,000 people were killed is really quite remarkable. And that is because Japan is the most earthquake-ready country in the world, and they are the most earthquake-ready country because they learned the lesson of this Tokyo earthquake in 1922, I think it was. Turkmenistan, 100,000. In Italy, in some countries in Europe, basically you can hopefully see that there's this swath that runs through Europe and across into China. So this is a collision belt. We'll talk about plate tectonics. This is where the plates are colliding, the Eurasian plate to the north, the African plate to the south. And so this collision of plates is what generates this belt of seismicity, which of course, and also the fact that there have been large numbers of people living in that part of the world for a very long time is the reason for very large numbers of fatalities in this region going back for many, many centuries. And then skipping over to the Americas, South America, Peru, the Peru earthquake here, 66,000. This is the 1985. It's called the Mexico City earthquake. The earthquake was actually offshore, about 300 kilometers away from Mexico City, but caused very strong shaking in the city, a lot of collapsed buildings, and I forget the number of fatalities, but I think it was like 20 or 30,000 people died in this particular earthquake. And of course, we spent a lot of time focusing on California, and the 1906 was a big deal, but in the global picture, this is a very small blip, as you can see, compared to the number of fatalities in other places around the world. So when you go and you add up all of these, the total number of fatalities in the previous century, in the 20th century, was about 2 million people. I just told you that in pretty much the first decade of this century, we are at about 800,000. That's almost half the number of fatalities that occurred in the entire previous century. So the beginning of this century has not been a particularly good start when it comes to earthquake issues. So is there a growing earthquake threat is the question. Is there a reason that this number is bigger? Is the threat actually increasing? And so this is a recent study looking at the number of fatalities using the best information that we can pull together from the historic record. And so these are just cumulative number of fatalities, the dots and the triangles, the circles and the triangles, are cumulative number of fatalities starting at whenever their catalogue started. And so this catalogue started at the beginning of 1900. It's the USGS catalogue. And this catalogue started, what is that? That's the same sign we use for our earthquake early warning system. If it was these guys over here that were beeping, I would be getting concerned. Okay, so this catalogue started at 1900, okay, and this catalogue starts at 1968. So that's why these sort of numbers are different. But what matters is the rate. Okay, so you can see that these two are very similar starting at this point in time. So they have very similar numbers for the last almost 50 years. Okay. And so you can see that there's lots of earthquakes, but then there's the ones that have a large number of fatalities. This particular earthquake here, for example. Another one. This is actually the 1985. That's the Mexico City earthquake. And then these ones are the ones that have occurred essentially since the beginning of this century. So you can see that there's a rapid uptake in the number of fatalities that we're seeing in earthquakes. To give you some context, this solid line is world population. Okay, so world population, of course, is increasing, but you can see that the number of fatalities is increasing at a much more rapid rate than global population. So this isn't just simply that there are more people on the Earth, therefore more people are affected by earthquakes. This is actually a change. A larger fraction of the people on the planet are being affected by earthquakes. Okay? So that's a reason to be, more reason to be concerned. And I guess these are the same earthquakes that we were just talking about, but these are some of the big upticks that we're seeing on this particular diagram. Okay, and the reason for this increase then is because we are seeing more earthquakes, what we call more catastrophic earthquakes. A catastrophic earthquake being an earthquake with more than 50,000 fatalities. It is not that there are more earthquakes. Okay, that's very important. There's no evidence for an increase, decrease, any significant change in the number of earthquakes that we're having. That is not what is going on here. What is going on here is we've had more earthquakes that occurred close to large populations that therefore resulted in a large number of fatalities. So we've had more catastrophic earthquakes. And so this plot just shows the catastrophic earthquakes going all the way back to the last 1,000 years. And so what's important here is that all of these dots that are basically on top of one another, these are all of the catastrophic earthquakes that have occurred in the last century, the last decade, and it's sort of it's much more rapid than the number that have occurred in the previous century. Okay? So why is this? The truth is that we really don't understand why this is, which is kind of alarming. One of the common hypotheses that people like to talk about is that so it's not due to an increase in the world population, but it could be due to an increase in the density of the population. We have more larger cities. So basically people are moving from rural areas into cities. So we have these high concentrations of people in cities, and then when you have an earthquake that's close to a city or under a city, you get a large number of fatalities because of the density of people. So that's a hypothesis that's out there that is very popular. The catch is that the rate of fatality increase is actually slower than the rate of city growth. So if the reason that we have this increase is because of people moving from the rural environment into the urban environment, then in fact we can expect the rates of increase to get even higher. Okay? So we are moving into cities more rapidly than the increase. So we don't fully understand why this is, which in a way makes it even more of a cause for concern, okay? Because we don't really know what direction this might be going in. Any questions before we move past these numbers? Okay. All right, so that's the historic record and some context from the historic record. But so now we sort of talked about fatalities, the historic record, and how the historic record is associated with fatalities. I want us now to sort of scale back to the science, as it were. And when we talk about the science, what we really want to understand is the true rate of earthquake occurrence. Okay? I already told you it's not changing significantly. How do we know that? And of course, it's not by looking at the number of earthquakes that cause fatalities. It's by looking at the number of earthquakes. Okay? And so if we want to look at the number of earthquakes, then we need to be able to map the earthquake occurrence with an even distribution over the entire globe. We need to know every earthquake greater than magnitude 5 around the globe. Okay? So that requires seismic observatories, that requires instrumentation to be able to record these earthquakes and to locate the earthquakes. Now, we've had seismic observatories since the early 1900s, and so the 1906 earthquake here in San Francisco was actually recorded by observatories in Japan and observatories in Europe, in addition to our own observatory here, of course. So Berkeley actually installed the first seismometer in the Western Hemisphere in 1887. Okay? So we think of that as being actually when the Berkeley Seismological Laboratory was born in 1887, and it was the first installation of a seismometer in the Western Hemisphere. And that was, so following that, obviously that was the first in the Western Hemisphere. Following that, more instrumentation was deployed in Europe. So of course we say the Western Hemisphere, there was already instrumentation in Japan and in China at that time, and it was basically then spreading around the globe, and so we installed some here in Berkeley, and then more was installed in Europe. And as time went on, obviously the number of observatories increased. By the 1960s, there were 700 observatories around the world. So what is an observatory at the time? That it was just as important that you had instrumentation and you had people who were looking at it. These were paper records, okay? And so if we call them observatories because it's an entire lab, essentially, to look after, to maintain and monitor the equipment. But there were about 700 of these around the world by the time we got to the 1960s, and that's how we were able to start building up global maps of earthquake occurrence, okay? And so this is an early map of earthquake occurrence. These are earthquakes, I guess it wasn't that early actually, this is 2002, sorry, my mistake. But this is now starting to show you these are large magnitude earthquakes. It actually doesn't say what magnitude it is, and I forget. But these are large magnitude earthquakes over essentially a period of about 1 century. So this is where we need to go if we want to understand the earthquake process, is to be able to measure earthquakes everywhere around the globe, okay? Then in the 1960s, the reason I said 1960, in the 1960s there was a complete change. We went from a series of individual observatories, so each observatory, like the Berkeley Seismic Lab, would have their own instrumentation and their own ways of doing things. In the 1960s, we started to deploy a worldwide standardized seismic network, standardized being the key thing. So the idea was to have a global network of observational instrumentation that was identical, because that way we can make coherent observations of the same earthquakes from different locations, and we can compare the observations of these different observatories. So this was a big step forward to standardize the seismic network. You can see it was deployed very rapidly over the course of 3 or 4 years, went from 0 up to about 110 stations. Anybody know what was motivating this network? Early 1960s? The golden age of? Right, it was the golden age of the nuclear test. Okay? So the reason that this network was set up was because the number of nuclear tests was increasing, and there was a need to monitor on a global basis these nuclear tests. Nuclear tests put out, they're not as big as earthquakes, or at least they're not as big as bigger earthquakes. A 1 kiloton nuclear test is about the equivalent of a magnitude 4 earthquake. So as people were doing more and more of these nuclear tests, there was a need to create a global network. This network was global, but it was driven by the US. And so there was a need for a global network to monitor nuclear testing activities around the world. So it was not earthquakes that motivated this network, unfortunately. It was the nuclear testing efforts that required this network to be deployed. This was deployed in the 1960s. One of these stations was right here in Berkeley, in a tunnel that is up in Strawberry Canyon. I guess it's that way. Up in Strawberry Canyon. We still use that same tunnel that's drilled into the side of the hill for our instrumentation today, although obviously it's not the same instrumentation that was put in the 1960s. So that was the first global network which allowed us to start to really map out global earthquake activity. This sort of decay here is because of instrumentations going offline. In 1985, the academic community got together and started some global programs, and one of them was the Global Seismic Network, the GSN. And so the Global Seismic Network was begun, and the size of that Global Seismic Network has sort of been increasing ever since. And so now the global, this WWSSN network, of course, is no longer used. It's the equipment is way behind, obviously, and now we have a much more modern network that is maintained by the academic community. So now there is an open academic global network of instrumentation, and the data is open to anybody. You guys can download the data if you want to.